Welcome to this tutorial. I will be taking you through introduction to bridge design in Eurocodes, and I will try to be very brief so that you can finish this tutorial within the next 10 to 15 minutes. So to enable me to do that, I prepared a PowerPoint to enable us to fast track this process and learn as much as possible in the shortest time span. So the design procedure that I love using is the ultimate limit state, and then I check for the serviceability limit states. But in this tutorial, I shall just be covering the ultimate limit state. So this is our model. It is a textbook model. I do not want to change it, but we shall just use it the way that it is. But in practice, I prefer using a minimum thickness of at least 225 millimeters for the deck slab. So in this tutorial, we shall just be covering the design of the deck slab, and then in the upcoming tutorials, we shall deal with other members. So as you know, this is the deck slab, these are the bridge girders, and this is the parapet, and this is the footway, and then we have an surfacing of around 150 millimeters thick for the purposes of this tutorial. And the depth of our footway is 270 millimeters thick for the purposes of this tutorial. So loading, as you know, in any structure, we have the dead loads, those are the self weights, and the live loading, that is the traffic loading. And the partial factors of safety for Eurocode, we use 1.35. So these are just the normal nominal weights that as an engineer you should be aware of. So this is concrete, which is 24 kilonewtons per meter cubed, reinforced concrete, 25 kilonewtons per meter cubed, and AC, 23 kilonewtons per meter cubed. So the deck design dead loads. So I prepared an Excel. So for the element, the parapet, we have the parapet walling, the deck walling, the footway, and the surfacing. So for the parapet, this was our unit weight. So this is our nominal load. The deck was 160 millimeters thick, so it is going to be 0.16 multiplied by 25 to get our kilonewtons per meter nominal load. For the footway was 270 millimeters deep multiplied by 24 for the concrete, and for the surfacing it was our surfacing was 120 millimeters deep multiplied by 23 and multiplied by a factor of 1.55 to cover for the resurfacing. You know, in bridges we design them for like a period of 100 years, and in that period the bridge must be resurfaced at some point. So to cover for that additional weight, we usually add 1.55, a factor of 1.55 to cover for that. So we get our nominal loads from these ones, and then we add our factor of safety, and then we have our ultimate limit state load, which we shall be using for our design. So this ultimate limit state load, this is the way we shall be applying our loads on our bridge deck. So as you can see, for the footway, as you can see, this is the deck self weight, which is 5.4 as we determined from here. This is the footway loading as we determined from here, we had a footway on both sides, and this is the surfacing loading as we determined from here. And this is our parapet loading, which we shall be applying as a point load. It was 0.68. It was 0.68 here. So that's it for the dead loads. So next we shall go to the design traffic loads. So in Eurocode we have 4 load models, that is load model 1, load model 2, 3 and 4. So the load models are applied on notional lanes. So for a carriageway width of less than 5.4 meters, we shall assume one notional lane with a width of 3 meters, and the width of the remaining areas shall be the width of the carriageway subtract by the width of the notional lane. So between 5.4 meters and 6 meters of a carriageway width, we shall be having 2 notional lanes, and then the width of the notional lane shall be W divided by 2, and then the width of the remaining area shall be 0. For a carriageway width of greater than 6 meters, so we shall calculate the number of national lanes using this formula. So the national lanes must be an integer. You take the width of the carriageway divided by 3 meters. So the width of the national lane shall be 3 meters, and then n shall be the number of the national lanes, and then to get the width of the remaining area, you shall take the width of the carriageway, you subtract the number of the national lanes multiplied by the width of per national lane. So load model 1, these are the adjustment values. This table is as taken from the Eurocodes. So we have lane 1, lane 2, lane 3. So as you know, we apply our loads on national lanes. These are the national lanes. So these are the factors that we apply on our loads. So for lane 1, these are the tandem axial loads. So these are the axial loads that we apply on load model 1. For lane 1, we apply 300 multiplied by 1. For lane 2, we apply 200 multiplied by 1. For lane 3, we apply 100 multiplied by 1. And then for the remaining areas, we do not have load. And then for the uniformly distributed load, according to load model 1, these are our uniformly distributed loads that we shall be applying per lane, and they shall be factored with these factors before application. So application of load model 1. This is the way load model 1 is supposed to be applied on our lanes. So this is your carriageway. This is lane 1, 3 meters. This is lane 2, also 3 meters, or as per your calculations from above. And so we shall, so these axial loads, so this is load per axial. So this is our axial. From here up to here, that is one axial. From here up to here, that is another axial of a vehicle. So this is a standardized vehicle that Eurocode uses for analysis. So this is another axial load, this is another axial load, this is another axial load, this is another axial load. So these are just representative vehicles that are moving towards this direction or this direction along the lane. So The distance between is 1.2. The distance from the curb is 0.5, 0.5, and then the distance between our standardized wheels is 2 meters. So this is how we apply our loading. So for load model 2, so this one we usually use it for local analysis where we require to test for a wheel loading. So the load model consists of one axial load of 400 kilonewtons. So per wheel it is 200 kilonewtons. So the same thing here for like load model 1. This is load model 1. We shall be using lane 1. It is an axial of 300 kilonewtons. So per wheel it is 150 kilonewtons, 150 kilonewtons. So for the axial it becomes a total of 300 newtons. So for load model 2, this is 200 kilonewtons, 200 kilonewtons. So our axial becomes 400 kilonewtons. So only one wheel of 200 may also be considered if relevant as a wheel load for local analysis. And this is usually the major application of the load in most cases that you will be using in your design life. So for load model 3, this is the one that we actually use for designing our bridges. So in Kenya, we normally use SV100 for normal bridges and SV196 for major bridges. So in this tutorial, we shall cover SV for the design, but I shall be using it for the design of girders since that is where I will find it applicable. But for the deck, I will just be using load model 1 since load model 1 contains the critical axial load that I will require of 300 kilonewtons compared to the maximum of 180 that is contained within SV 196. So for the deck design, we shall consider the critical axial of 300 kilonewtons in load model 1. That is for lane 1. That is the one that I found that will give me the kind of loading I require for the ultimate limit state. So these are just special vehicles for load model 3 as we find them in the Eurocodes. So application of load model 3. So SV and SOV loads are first multiplied by their dynamic amplification factors before being applied. So these are the basic axial loads, these are the dynamic amplification factors. So load model 3 is usually applied in a combination with load model 1. This combination is sometimes classified as a load group GR5 for those who love to use software modeling. So we shall go to the application of load model 3. So this is the direction of travel. This is how I like applying my load model 3s. Of course, there are some other ways to apply them as seen in the Eurocodes. Let me open the Eurocodes. So this is the national annex, the British national annex to the Eurocodes. So the other ways for applying load model 3. So these are the other ways that we use for applying load model 3, but in practice, we mostly use this one. Okay. So load model 4. Load model 4 consists of a uniformly distributed load for crowd loading. So this loading is more relevant for bridges located in or near towns. It is represented by a uniformly distributed load of 5 kilonewtons, which includes dynamic amplification. So these are the groups of traffic loading which we usually consider in design. So as you can see, we mostly use group 5, which is usually sufficient for our ultimate limit state. So group 5, we consider load model 1, frequent loading, and load model 3, characteristic loading. So application of traffic loads to our deck. So for lane 1, so our deck was having 2 lanes because as you can see our deck was 7.3 meters. So and then if we divide it into national lanes, we shall go to our national lanes formula. We shall go to our national lanes formula, which is around here. So this is where our deck falls. So we shall be having, so the number of national lanes shall be our carriageway width divided by 3, which we shall find is 2 with the remaining area. And the remaining area shall be around 1.5 meters. So that is how I have represented here. So this is the tandem loading and or the axial loading, and this is the UDL. So for lane 1 we shall be using 300 and the UDL is 9. So these are values we find from this table. So we come back to our table for our load model 1 table. So 309, and then we factor them. So we factor 300 by 1, and then we factor 9 by 0.61. So that is what I have done here. 309, I have factored them 1 and 0.61, and then I have added the factors of safety to find the ultimate limit state loading on that lane. So for lane 2 the same, and for the remaining area the same, to get the ultimate limit state loads. And then for the footway we take 5, so there is no factor because as we read, this loading so it is represented by uniformly distributed of 5 kN, which includes dynamic amplification. So the load has already been amplified. So we don't need to amplify it here. And then we add a factor of safety. Then we get the ultimate limit state load that we require for our analysis. So we load our deck. So starting from the footway we had 6.75 on both sides, and then the footway was covering from here up to here. So we load it in, and then we load it in. So this is and then we come to the traffic loading. So this is the UDL, the uniformly distributed load. So we had 7.41, 7.43, and 7.43. So I just decided to use 7.43 for it to be uniform. And since it is slightly greater than this one, so I just think 7.43, applying 7.43 uniformly will work, instead of applying 7.41 for lane 1, and then so now it's It's also more than 7.41, so it is safe to just apply it throughout, and then we applied our tandem loading. So here we had 405 per axial. So this is our first axial. As you can remember, for load model 1, let's go back to load model 1. We leave a space of 0.5 from the curb, and then we apply our first wheel load, then 2 meters, and then our first wheel load for that specific axial. So that is just what I did here. I left 500 from the curb line. I applied 203, which is just 405 divided by 2 to get a wheel load for that axial. So 202, 202. And then I left 1 meter between the loads. And then I applied for lane 2, 270 divided by 2. You get 135, 135. So this is our first notional lane from here up to here. We have applied our traffic loading. This is the second national lane from here up to here. We have applied our traffic axial loading, and then for the remaining area, we do not have. So I combined this loading to look like this for easier analysis, since I do not want to do the dead load analysis on another separately from the traffic load analysis. So I just combined it into just one drawing where I did where I shall be using it to do my analysis. So my software of choice for this analysis was F-Tool. So it is a very lightweight software, and I find it that it comes in handy when doing these small things. So let us apply our loading. So we start with creating our points. So first click this one, and then now you create your points. So the first one shall be 0.9 meters, 0.9 meters. Okay, it's there. The first point shall be at 0, so it's there. This is 0.9, and then the next point shall be 0.9 plus 1.5, 2.4. The next point shall be plus 1.5, 3.9. The next load shall be at plus 1.5, 5.4. Okay, the next load shall be at plus 1.5, 6.9. Okay, the next loading shall be at 8.4. Okay, and then 9.9. And then 11.4. And lastly, plus 0.9, 12.3. So we have all our points. Let's put our beam or our slab. So that is our slab, it's ready. So let's define our material properties. A new material shall be a concrete bridge. Concrete, done. So shift key, select all our members, and then you shall apply. We apply the material. Section, create a new section, rectangular section, done, a depth of 160 millimeters, and then you assume 1 meter. B. Choose our sections, apply. Then we apply the support conditions. Okay. Apply the support condition. Apply. Now the next thing is to apply our loading. So the first loading shall be 0.68 for the parapet loading 0.68. So you come to the point loading. You create a new loading parapet. Done. Going to be negative 0.68. 68 kilonewtons. So you click that point, apply it. Click that point, apply it. Next, it is the footway loading. So the total UDL for the footway loading is 6.75 plus 8.75 plus 5.4. You get 20.9. So you create a uniform loading. This is the uniform loading. Create a new loading. Name it footway. Done. Then it was 20.9. Negative 20.9. Select your members. Apply. Then let's come to the center uniform loading. It's going to be 5.4 plus 5.78 plus 7.43, 18.61. So you come, create a new loading, deck UDL, done. Negative 18.61. You select your members, apply. And then we come to our traffic loading, which is point loads. So we shall start at 103, so we shall add new points. So the first load is at 0.9 plus 1.5 plus 1.5 divided by 2. No, it's going to be 0.9 plus 1.5 plus 0.5 at 2.9. So it's going to be at 2.9. And then the next one is going to be 2 meters from 2.9. That is going to be 4.9. 4.9. The next one is going to be 1 meter from 4.9. So it's going to be 5.9. And then 2 meters, 7.9. And those are all our loads. So let's apply our point loads. Come to the point load, create a new load for lane 1. Let's name it lane 1, done. Negative 103. Apply. Apply. Create a new load. Then 2, done. It is 1.5. Negative 1.5. Done. Done. And then we analyze. So we name it tutorial. Save it. Then we have our moment diagram. So as you can see, this was the same moment diagram that I was having. And then this is the shear force diagram. And from this diagram, you can calculate the reinforcement from, so we have the moment, you can calculate K, and then you can calculate, and then we provide T16 to at 150 both sides. As you can see, our area of steel is this is our area of steel, and the nearest is T16 at 150 is the one that is most appropriate. So that's it for today. See you on the next tutorial. Thank you.